I've left the last part of the review. It's the field theory associated with Chapter 10 of the review unit. And I'm going to give you another way to look at exponentials, particularly as they apply to analyzing two-dimensional fields. And we'll probably get about halfway through. The very dense stuff at the bottom will be the following lecture. But today I just wanted to get you some idea. And if you become teachers yourselves, I think this is some stuff that you could use very well for even at least this first part at the high school level, but certainly in college and university. And the main idea of the whole thing is what good are complex functions, exponentials, and so forth. And so I'm going to go through about 16 reasons why these things, this mathematics of Euler basically, really helps us in physics. And that will be followed in Unit 4 by the generalization of the exponential functions, that is the quantum mechanical spinor analysis that occurs for resonances, first of two-level systems, but then also for other things. So let's just go ahead here. Now the disadvantage of all of this is that we do not have the application which draws these diagrams that we'll use in this class on the web. It's still an old-fashioned system, OS 9, and kind of stuck there right now, and uses some weird programming that's a little difficult and tedious to get onto HTML. But we're working on it. And in any case, it really starts with greed. That is banking at its worst sometimes, when interest rates go very high. And I spent several years in Brazil where we had the interest rate hovering around 100%. And that's an interesting experience, which I would not want to repeat. But in any case, we're going to just take the interest formula and show some things about the numerics of that, and then extend that to Taylor-Maclaurin series and things like that that we need for physics, and how it helps you do calculations. So basic idea here is that if you have simple interest, you have a rate, let's say it's 100%, so take a rate of 1 right there in that formula. 1 plus r times time becomes a principal. After the year has passed, you get $2 from 100% interest. So question then is, how does compounding increase that capital that you earn after a year? And so at the half period, you've done simple interest, then you do it again. And so you get a product of 1 plus RT over 2, and come up with 3 halves times 3 halves is 9/4. So you come up with not $2, but $2.25. That's a big jump from just simple interest. And as you continue this and say, what if we do it at a trimester? That's 3 of these factors, now each with a fraction of 3 in there. That's a pretty big jump too. You get $2.37 at the end of the year with that one. And so you might think that, oh boy, I can entice people to go to my bank if I do what it would be called infant interest. So you make little symbols with an infinity bow tie and a big cigar that you're going to be smoking after you get so rich, by running your compounding rate toward infinity. So the catch is, of course, that you don't get much more or at least a whole lot more than $2.37. And so we'll go and list kind of the examples here for first our simple interest. We picked up 25 cents going to trimesters, and when you go to quarters you get $2.44. You can see the amount that I'm adding here plus 7 cents isn't much. Then if you go to monthly, that's a really big jump in computation. You got to multiply 12 times now. That still hasn't increased you very much, but you do pick up 20 cents or so, and so forth. And at a certain point here, the gains are way down in the decimal place, the fourth decimal place. If you're going by our standard calendar, weekly, okay, that's 52 multiplications. Daily, that's 365. If I'm going to do it hourly, that's 8,760 compoundings that you would be doing to get. And I think you recognize the number in green there. So that's a really amazing limit. I find it very, I mean, anything that has to do with E that involves limiting is I think, some, sort of beautiful. And one of the problems on your weekly problem today is to tackle one of those problems. In any case, the idea is that you do find. Now, this is an amazing number for other reasons. It's 2.71828. Then it does 1828, and if you just stop there, you think, oh, I must have a rational number here with continued thing. You don't. And the continued fraction of this number is very interesting, but after this 28 right here, it's 4, 5, blah, blah, blah. And the idea is I'm doing this with a power that's approaching infinity here. I'm doing it in decades, first 1,000. That gives me 3-figure precision. If I multiply 10,000 times, I get 4 or maybe close to 5-figure precision, and so forth. Doing it 100,000 times gets me, say 10 to the 5th gets me 5-figure accuracy, and so forth. 1 million, it gets 6 figures, 10 million, so on and so on. Here I have a billion, okay, and I get a 9-figure precision. This is definitely not a very efficient way to calculate E, unless you've got a really fast multiplier, okay? And we do have fast multiplier. That's done very quickly on most computers, right? But doing any calculations that involve that over and over again is not good. So the improvement of the computational efficiency of this is the key to breaking this log jam here. And so this binomial here being expanded, that's the key to solving this. And then using the factorials, but taking the limits of the combinatorial coefficients here. When I'm up at a billion here, I can throw away on a thing like that everything except the n cubed. And so that's basically what I'm doing here. As I'm approaching infinity, I'm letting each one of these numerators of the combinatorial be just the highest power, because the next highest power is down by, well, if I'm doing a billion, it's down by in the 9th figures. So that then leads a very famous series that you've probably already memorized. And I want to have a look at series like this before we go too far here. How good do power series really work for the kind of functions that you run into in classical mechanics and quantum mechanics? This is looking at, how well does perturbation theory work when you're doing a power series of that? So here we go, and using this, I can get some pretty good precision here, say 4 figures. It took me 10,000 or 100,000 multiplications. I can get it just by 1, 2, 3, 4, 5, 6, 7, or 8 terms of very simple arithmetic. So that's a big difference, this to this, you say. An important difference, as you probably already realize. Anyway, when somebody asks you about what do you get at infinitely compounding $1 at 100% interest, the answer is $2.71.828 cents. Okay, that's worth knowing if nothing else. Okay, now let's just take a look at a general function. Once again, I want to go through the thing where we scan the derivatives for first terminology, but also the algebra that goes with it. So if I have a series like this, a power series like this, and I ask, well, what's the velocity? Okay, I take the first derivative, and then I take another derivative to get to acceleration. We've already been through this with respect to the sines and cosines that go with the oscillator. Okay, so this is for a general power series now. And we're going to marry that to the oscillator, obviously, but that takes some time. And then, of course, we come here with the change of acceleration. That's the NASA terminology for that. A moment of honor for Colonel Stapp that experienced this, the high values of both of these. But in any case, that's what we have to do. And then I got silly like NASA called the next one the inauguration, and so forth. So each time you're getting another 1 over n factorial times the initial value of this. So this is a Maclaurin power series. It's a Taylor series around origin. Okay, and you should, if you're teaching UP1, it's a good idea to show that this is just part of that series. You have the initial position, you have initial velocity, and if you have constant acceleration, you don't bother to put the 0 here and have another term. So that's, I think, important. The good old UP1 formula is hiding in the Maclaurin power series. Okay. Now the exponential, very weird, and all of this is kind of weird because it's really saying, if mathematics was really sort of, shall we say, anally perfect, then all I have to do is get all of these numbers and I predict the future from one point. Well, what's wrong with that statement? You see, that's a thing that you have to ask about a lot of things we do in physics. You know, how well can you predict the future? Extrapolation is what it's called. You know some things about these numbers, what's next? Okay? And the exponential is really weird. So, you know, kind of every morning when I get up, well, not every morning, but some mornings when I get up and sort of wake up, it's kind of like that. You are slowly putting together your consciousness and thinking about, well, I'm going to get up, not now, I'll get up next. No, and then you say, I'm now, and so on. Each time you're putting another number in this series, you see, finally you get up and behave normally. But there is that sort of breakthrough from time equals 0. And it's good to see it geometrically, and I want to see this for the sines and cosines. I want you to see that because I don't see it in any of the other textbooks that I've come across. And it's so easy to plot it, so why not? The idea is the linear approximation to the exponential 1 plus t is that purple line there, and it connects with the exponential pretty far. But the exponential is this red curve here, you see, and all of these things are trying to get it from the bottom more and more. All right, so if I add one more, the quadratic, the parabola plus the line plus the constant, okay, so there's the constant, just sit there and gets 1 point. Then the line gets a few more pixels, and then the parabola gets a few more right, you see. This is the hopefully convergence to the whole function eventually. And quadratic, the cubic is next, and then you can see in just without color how these things are slowly approaching this curve. Now this is the story for cosine and sine. This I found this quite remarkable. Let's take the cosine because it starts with a quadratic, doesn't have any odd powers in it. It's an even function. This guy's an odd function, so he has only odd powers in him, zeros for the evens. They all behave in pretty much the same way. And the parabola is a pretty good approximation to a cosine if you turn it over and put a minus sign on it, which is that minus right there. But then you don't do anything until you go to the fourth power, and the fourth power takes you to a 1 pixel accuracy from here down to about there. You see, and then the fourth just takes off and says, heck with it, I'm not going to do this curve. All right? And then the fifth, the sixth, the next one, takes you just a little bit further. You can see it's sort of coming loose right there, and then boom, it's gone. You see. So there's this sort of explosive place where the thing just says, I give up. Eighth approximation, eighth order approximation, that's the sum of all of these terms right there, gives this, you see. So it carries you from about here all the way over to here. So it takes 8 terms of this thing to get pixel accuracy, whatever that means, and you have to scale this thing accordingly. But it's giving you one complete oscillation. It's 8. That's kind of, anybody tried this before? Have you ever done this trick here? It's worth knowing, okay? And what's really remarkable is then 16 gets you 2. It's kind of linear. The spacing between the peel-offs is pretty much constant. And that's true for the sine wave here. It has the first, the third, the fifth, the seventh, about the same number of things in order to approximate it for one complete oscillation. Okay, that's something that's worth knowing. We'll be bringing that up from time to time. And as I say, the thing that's really going on here, if you're thinking exponential, is some kind of internal fraud in the bank. This is where you have imaginary accounts, second books, right? And that means you have imaginary interest. So by putting an I in that exponential, and then splitting it into I times the sine and cosine. So this is Eulers Formula, you see, being pulled out of the series. And we've got to do this again for the spinners. That's what's coming in Unit 4. Okay? But I wanted you to see all of the two-dimensional magic you can do with this before we take it into, it's really 4 dimensions. That's the next stop. The spinners take care of relativity as well as ordinary rotations in 3 dimensions. We're going to do today just using this formula, you know, a lot. Involving 2 dimensions. Motion in 2 dimensions, fields in 2 dimensions. So there's a little picture of what we just looked at for the sine and the cosine. And of course, if we're going to talk about things that oscillate, we're going to use a phasor. So we're going to use something that has e to the I minus omega t, and goes clockwise for reasons that we've talked about, and that is true for any phase space. They all go left-handed if they're oscillatory, stably oscillatory. Okay, so what I want to point out also is the bookkeeping, how this whole business simplifies the bookkeeping. For example, you're on an exam and you're stuck and I can't think of what sine of a plus b is, or cosine of a plus b. Well, it's much easier to remember that e to the I a plus b is just the product of the a and the b, right? So you expand that. Bingo, you get both the sine of a plus b and the cosine of a plus b. That's the imaginary part, that's the real part. Okay, so, you know, when these are little tricks if you're going to be a teacher, you should show this as early as you can. So students, complex numbers add like vectors. A quick derivation of the so-called cosine law, it comes out quite nicely with this. When you sum these two, you're just doing that, and when you're taking the difference, you're doing that, and so forth. So these are shortcuts. These are nice shortcuts to do things that we use all the time in elementary as well as advanced physics. And then tracking position and velocity on a phasor clock. I've already mentioned that. There's the clock. I say the real part is where your is, the imaginary part is the gonna be. Okay? Or another way to say it is imagination precedes reality by exactly 1/4. That's a business maxim that is not very nice because it retards creative thinking. But in any case, this whole idea of using complex numbers, the phase, angle, or argument, that's a terminology that you'll see a lot, and the magnitude or modulus, that's this little guy here where we take the psi star psi. That's so important in quantum mechanics for getting probability. We'll be talking about that enough. So anyway, the conversion between rectangular and polar, which we've already done when we were discussing that coordinate system. And by the way, coordinate systems are the main topic today, behind the scenes sometimes and in the front of the scene a lot. So these relations here are pretty important. And this is a really tricky one, the arctangent. And if any of you know, are doing programming, you know that A tan is not good because it doesn't know what quadrant you are in for sure. A tan 2 requires that you give both the x and the y separately, not their ratio. If you do that, you don't screw up what quadrant you're in. So the A tan 2, how many people have known about that as you do programming? Have you seen that one? You've probably seen it once or twice. See it more than that whenever you're doing any programming. Or if it's a high-level language, you just do a conversion of polar, and they already have that built in. You know, calculators have an x, y, and then they have an r theta on them. They're doing that essentially. So that's important. Okay, now let's get into the idea of the vector algebra and then the vector calculus. Here, what I'm trying to show is that if you multiply an exponential times a complex number, there's the x plus iy of z. That's our standard notation for every discussion like this that I've seen. And then you come with e to the I phi, our cosine plus I sine. You get this for the real part and this for the imaginary part. Okay, that's easy to work out. But what you're doing, you see, is in Gibbs notation, is you're taking a rotation matrix, okay, of xy, you see, and you're getting those two components. There's the real part, there's the imaginary part. So the idea of this e to the I phi as a rotation operator is really essential. And it plays out right here. This matched with that, okay? But this is the way you write it. It's so compact. This is a lot of extra notation. And this has got it spread out in 2 by 2 structure. But you can begin to see how complex numbers are excellent bookkeeping. Shorthand, that's powerful, okay? So that's what happened here. This cyan e to the I phi acting on the dark blue z has just moved it up, rotated it. That's the geometrical picture of this, which all of this should be, you know, sort of interchangeable for your thinking if you want to be efficient with this thing. And it continues on to the idea of a dot and cross product. Okay, how would you introduce that to somebody who was just learning this stuff for the first time? Which I hope you're not, but you can easily sympathize with being able to cut across the boundaries here. And that involves the star, which is the complex conjugation. So when I put a star, and that's true of all literature, when I put a star sort of as a subscript of the thing to the left, that means convert that to something with all the i's changing sign. There's only one I in this particular one, so it gets a minus. And the b just continues on as though nothing had happened. But when you multiply these two together, we're going to do this trick over and over again for the next 15 or 20 minutes as we start going into the calculus of the vectors. you produce here an ax bx plus an ay by that you recognize immediately as a dot product of a and b. And then the imaginary part is this crazy thing, and this one I have to say a little bit about so that we don't get confused later on. But that is a z component, where z is, and now I'm talking about great big capital Z, it comes out of the board. That is the third dimension that complex variables, for the most part, ignore. But because the big Z component, perpendicular to x and y, it's the cross product with that suffix or prefix, postfix. Okay, this is the number here, ax by minus ay bx, in that order that was given to us by this product. Okay, so we're going to be working with the real part, which will be a dot product of a product, and then the cross product comes up as the imaginary part. That's, you know, that's worth knowing, and as you'll see when it comes to doing differential calculus of vectors, yeah, and then integration really is cool there. The bookkeeping is pretty neat. So the other thing you can do, of course, is to always rewrite your complex numbers in polar form. If you do that, then the exponentials add, one of them being minus because it got starred, conjugated, and the other one just sitting there like nothing had happened. And then you get the product of the magnitudes, and then the argument is this difference here, you see. So go ahead and expand that like we did, and you see A dot B and A cross B once again in that form. Okay? So, you know, that takes you through the loop of the products. Now we got to do this over again for spinors in Unit 4. So there you are with Cartesian coordinates matching each of those. Okay, that's a complete loop right there. Okay, let's try the derivatives. Now this is a little bit tricky, and the thing that I'm going to do with it is a personal trick. That is a trick that I haven't seen anywhere. But given the fact that we can plot these things so easily, it's really nice to have. So the idea is the relation of the z and the z star, let's say, to be viewed as two independent variables, which is really crazy because how could z star be independent of z? Well, how can the Hamiltonian have an independent parameter from those of the Lagrangian? You see, this is a similar sort of thing. So we're treating them as independent variables, just like the independent variables which are obviously independent, x and y, the real part and the imaginary part of the complex number, z. Now we have to do this for the derivative. And then there'll be a star derivative of any function that you might have. And that function will be a function of two variables, either x and y if you want to write it that way, or z and z star if you want to write it that way. Okay, and in the process of doing that, of course, you have to have a conversion between those two ways of looking at the thing. So this sort of sets the independence right there with the relationship between x and y and z and z star. Okay? But we need one of those relations for the derivative. So what I do here is a weird kind of chain rule where I say, okay, I've got a derivative with respect, this is already a complex thing, and so is this z down here, but I just put it in place here as a partial derivative with respect to z. Now, what does that mean? Who am I keeping constant? Well, that's what's sort of tricky about all this. But what I've done is I said, I'm going to do a chain rule where I put these two aside and then stick partial x, and partial y in there, as you would for a chain rule that really was clearly delineating two independent variables. And if I do that, then I have a partial x with respect to z. I go back to here and see what that is. And by partial, I mean this is constant, that's varying. So I get a 1/2 right away. And the partial z with respect to z is 1. So I get a 1/2. This 1/2 is weird. Okay, and we're going to see how it plays its role in making complex variables very clear. But at this point, I have to wave my hands a little bit more than I normally should. And then the same thing happens here, partial y with respect to z. Okay? It's 1 over 2i, or minus I over 2. I go and do this one, I'm going to take the derivative with other independent variable z star. I play the same game, so I get this. Well, this is just the conjugate of that, as you might have kind of expected here. So we've got two kinds of derivative, dz and dz star, and we have to have in the background, so to speak, in all of this stuff that we're going to be doing with these as far as the differential analysis goes. So what we're doing here now is we're taking the chain rule that shows what the real and imaginary parts of df dz really are with respect to vector analysis, which is, you know, this is going to be a vector, fx, fy, some force of a vector, for example. Okay? But it's a force vector in a whole field. That's what makes this so darn powerful. So I'm just pulling these guys aside here to be used. I'm doing a ddz, so it's a ddz only. I'm not going to mess with that guy for a while. It means I put this guy in there, and then I just multiply it out. Okay, I've got a real part here. I've got an imaginary part here. And you should recognize those as divergence, two-dimensional divergence, and two-dimensional in the sense of x and y, but one component, curl. So you only have one component of the divergence because it's a scalar product. You don't have to put any funny writing there. But this one is the magnitude of the curl of f in the plane. Okay? And of course its component would be perpendicular, but we're not letting that happen. This is just a number. This whole thing here is just a number. And sometimes I'll eliminate all that stuff right there. Just I'll write it. Maybe put the bars on there to remind that that's a real number. Okay, is this clear so far? Because this is the big step to make all this field theory work. Okay. All right, now what you get from this is rather remarkable. This is a way to invent two-dimensional vector fields just from all the functions you know. You know the sine, the sine squared, z squared, 1 over z squared. Name anything as a function of z, tangent of z, whatever. You get a beautiful field out of every one of those if you follow this recipe. Okay, so the recipe is as follows. You can invent source-free fields. These are fields that have no divergence and no curl, so they're vacuum fields. You have all sorts of stuff around them, making the field as weird as possible, but the location that we'll be talking about inside the field is no divergence and no curl. That leaves you a lot of room to make fields. And coordinate systems, this is where you're going to learn how you derive various different orthogonal curvilinear coordinates, which sets us up for some mechanics later on. And there's a problem this week that has to do with the very simplest of these. So anyway, a source-free vector field that has both zero divergence and zero curl, you take any function of z, conjugate it, that's whatever, if there's any i's in there, turn them to minus i's, so that you get something that, probably would write as f star z star. And the thing about that is that that thing is only a function of z star. It's not a function of z. So the derivative with respect to z, which is what we just calculated here, is 0. That means the real and imaginary parts of that thing, which are the divergence and the curl, is automatically, totally 0 at all points x and y. That's the recipe. Okay, we can see some examples here. How about the easiest function, z itself? Or a complex number times z, but let's make it even simpler. Let's just set a equal to 1. Let's just do z itself. That makes a beautiful field, which is actually sitting on the screen down the row there. So what do? You say, okay, I'm going to replace everything in there. And if the A was real, I would not bother starring that. But I'm going to replace the Z with Z star. Okay? So this thing is not, it is by definition then, not a function of Z. So it has to have a 0 Z derivative. That means that this thing, the real part of that, is 0. And the imaginary part, the curl part of it, is 0. Sure enough, divergence, just from your own knowledge of the divergence, is this sum partial fx with respect to x and partial y with respect to y. That's giving us a partial ax here, but it's giving us a minus ay with respect to y here, nothing, 0. This thing right here also goes away rather easily. So what we're producing here, so some people call DFL, divergence-free laminar flow or field. That's a technical name that I thought was kind of cool, so I'll add it to the mix here. Okay, now I'm going to zip this guy ahead so that we have two views of all of this stuff here. There's the thing where we actually work out the integral of the thing, but before that, here's the source-free thing, and here's the derivation that we just did. Okay. And this one cuts off the fancy name for the field that you're going to get. Has no sources of curling, no little propellers making whirlpools, and then nothing is giving any source of the fluid that belongs to this thing. There's no outlets at the vacuum point, as it were, of this field. Okay, so this is what it looks like, and I'll have the machine actually draw this thing, and we'll talk a little bit about what this is. But you see that it's kind of neat. Just the simplest function, f of z, z itself has this beautiful structure. It's a quadrupole field. Okay, it's kind of neat. Now, what's going on here that's important to see is that when I write this thing, f with a minus sign, what I basically did, and I'm going to actually switch this over now so that it's running the old machine. This is the thing that lets you pick typical functions. Force field, constant, well that's just arrows all pointing in the same direction. This one right here, AZ, f of z equal AZ, okay? That's what we're drawing here. So I'm just going to go ahead and plot the darn thing. And let's see, there we go. I think it should, there we go. Okay, it woke up. All right. Now, basically it's kind of like the harmonic oscillator field. Remember that? Where wherever I was at a certain point, I'll say that was a position vector. Then the force vector would just be an extension of that. Say if I scaled them equally, it would be an equal extension. If I scaled it down a little bit, it would be like that. That's kind of what we have here, except by doing that conjugation, I turn it at right angles. That's the only difference between the harmonic oscillator field, which has lots of divergence. It's what you get when you're inside the Earth at all the sources of gravitational field all around you. Okay, what we're talking about here is something you get in a vacuum, a force field that here is turned to right angles, and then one down here, which would be a vector just like that, is reflected, you see, through the x-axis. Or a vector here, which would be pointing that way, is reflected down. These vectors are all unchanged, and then the same ones here. This guy right here is a vector down here. It would be right there if it was just plotting z. I reflect that. By doing that little reflection, I turn it into a field that has no sources anywhere in this neighborhood. sources are way up there, or way down there, and way out there, and way out there. This would be a sink down there, and a source up here, and a sink down here. That's the field of a quadrupole. Internal field of a quadrupole. Okay? 2 plus charges, 2 minus charges at right angles to each other. Okay? So that's what I wanted you to, invite you to realize that just z by itself makes a really beautiful thing. Now z squared, a little more complicated. That's on the far screen there. Okay? And then hiding down at the bottom here is, well, we'll get to that. Those are not the kind of functions we want. Those guys, that black and white one down there, it's got sources all over the place. Okay, but what we're making is fields that are due to sources outside of the region in which they live. Okay. Now, if this thing is a laminar, that's divergence free, curl free, then and only then can I find a potential that will give it just by taking a derivative of that potential. That's a z derivative, and it's complex, and this is a phi that's complex. But this thing is going to give us a field, a DFL field, okay, divergence-free laminar field, okay, and it is a gradient of a scalar field, or you can treat it as the curl of a vector potential, but a vector potential that lies in the plane. You see, that's the a curious thing about this. So we'll be dealing with a complex potential, and I have to derive this, but that's just setting you up for seeing where we're headed here, that this guy has 2 parts to it, which I'm going to color red and blue to just differentiate. I'm using standard notation for each of those there. So remember what the rule is, that we do a complex conjugate of this thing, okay, and the z star, the z derivative, will be the one that gives us the field after it's applied to the potential, this complex potential. Okay, so how do you find the complex potential for this thing? You see, that's kind of a difficult thing. It's really easy to go, the normal way would be to know the potential and then take the derivative and you've got the field. Okay, but going backwards, you see, that's the hard part of electromagnetism. And so what we're going to do here is we're going to somehow have to integrate this. Well, we're just going to integrate it like it's a real variable. That's the cool thing here. So if the force, the complex F, that is force field, is the derivative of phi with respect to c, it's kind of really small there, you might have a hard time seeing it, but the idea is that this phi, that's this real part plus an imaginary part, is simply the integral of that f with respect to dz. And we just use standard calculus formula. Az dz integrated is 1/2 az squared. Then you expand it. You expand the x plus iy squared. Real part, x squared minus y squared. Imaginary part, xy. Actually 2xy, but I had a 1/2. That's this 1/2 that will be bugging us for all of these things. So when I make a graph like this, and now I'm going to use the actual application here to show where the equipotentials are. For example, if I just click on the screen and it wakes up and draws a set of equipotentials for every point that I pick. I'm going to go close to the 45-degree line and make a really eccentric hyperbola, and then right next to that is another hyperbola that went down here. I don't know, can you see that from where you're sitting, the red curves, okay? And so everywhere you go, it just goes and integrates very easily and numerically where the equipotential, that's the constant voltage line, so the voltage here, the phi, is constant along that red line. It's minus 1.5 volts. So that's down. That area there is a downer, and I get the higher voltage here. That's let's see if I've got that right. This is minus 1.5. This is minus 0.67, and so forth as I approach 0 on this set here, or on one that's nearby there. And I'll try to get the 45-degree one if I can. That's a little tricky. It's hard to, one way to do it, just put it there and see if we can find it. Sometimes it can, sometimes it can't. There we go. That's the asymptotes for those hyperbolas. Okay? So, we'll go ahead and finish this thing. Get an extra one on there they didn't really need. And we'll make a few down here in the lower portion. And normally you would put these at equal intervals if you were plotting this thing. Now we're going to make use of this thing for other things here, but I thought we'd get started right there. Now, that takes care of the real part. You can plot both the real and imaginary parts at the same time, but I'm doing them separately just to make a point here. The other ones, the other side of the story, has the vector potential. And what is the vector potential? It's what the hydrodynamicists call the streaming potential for hydrodynamic flow. If all that green stuff was green water, kind of like some of the water you see around Arkansas in the hot summer, there's the flow lines. It goes along the flow lines, you see. This is a potential that most of us as physicists aren't that used to. The idea of having something that tracks the flow rather than sits along it, just the opposite. And of course what I'm making here is a coordinate system that is OCC, that is orthogonal curvilinear coordinates. Everywhere that flow line crosses the other hyperbolas, is a hyperbola that is orthogonal at every point to the hyperbola it might be crossing at any given moment. So that's the complete picture, sort of complete. I mean, I'm being sort of sloppy just doing it by hand, of this object here. And the idea is that when we do an integral from one point to another, it isn't going to make any difference what path I take between these 2 points. It will just depend on what the potential is here and what it is here. So the amount of force that it takes to go between these two is just given by subtracting potential here from the potential there. That's what it means to be laminar, curl-free, divergence-free flow. Okay. So I'm reminding you here that this is a coordinate system that's in the problem, part of a problem that you've been given for this week. Okay. Now, the next thing to look at is how do you describe the gradient and the curl in this half and half formulas. And I say half and half because you see that field can be made equally. I'm going to say this again, but I want to make it clear right now. That field can be written either as not 50%, but 100% of this, and just forget about that. Or it can be written 0 of this and 100% of this. That's why we have the half and half. You can go either way. You can be a hydrodynamicist and work with A. They're more familiar with A than probably they are with a scalar. And you're fine. You can work it that way, as long as you stay away from the sources. I mean, yeah, the sources, we'll talk about that in a minute. But this is the one that you'd be used to, and that's the one you'd use. So that's another tricky part of this, is the half and half. Either one. So I can go 1/3 of this plus 2/3 of that, if you want to mix it up. As long as it adds up to 1, these two numbers add up to 1, you're golden. It's going to give you the same number, same deal. Okay? So it's worthwhile proving that, but I just wanted you to be aware, be warned that that's what we're after here. So what I'm doing here is I'm actually taking the dz star, the star derivative. This is a star function. Remember, we have to star all of the functions that we work with in order to get this thing as I say, laminar, curl-free, divergence-free. Okay, so I'm going to do a dzz star. Remember what that is? That's got a plus sign in it, right here. Okay, so, and then I've got the minus sign in here because this is phi star. Phi by itself is just phi plus IA. All right? So we get this extra minus sign we carry around, but then the derivative that we use is the plus sign. So we got to take this thing and put it, sort of expand it, write it in terms of what the derivatives do to phi and what the derivatives do to A. And what you see here is a gradient. The idea being I have a partial derivative with respect to x of phi, and then the other component, the I component, the imaginary component, is the partial y with respect to phi. Remember, phi is a function of x and y as well as z and z and star. So you keep playing the two kinds of variables against each other, z and z star versus x and y. And then this crazy thing right here you recognize right away as the curl of A, but it's a two-dimensional one. It should have the little braces around it that says we're working with just one number for the curl, okay? But we're making a vector out of it in the two-dimensional plane. There are the two components right there, just as the gradient has two components. And that kind of completes the circle of the derivatives versus the functions. Needs to really have the integral thrown in. Okay. Now, you should notice something right away. This has been mentioned in this class early on when we first talked about force. This is the mathematician definition of force. No minus sign. Okay, so potential theory was developed essentially by people that would be more called mathematicians now than physicists, but everybody was called just a philosopher in the 1800s when this stuff got developed. Okay, physicist definition got the minus sign, remember? Well, we get rid of one minus sign. That's what minus signs up here to trip on, but this one we will not have tripping. So here's the idea. The gradient of this potential, this x squared minus y squared, is scalar potential, or the curl of the imaginary part of the potential, that's the AXY here, okay? Both of them give you the same answer. Work it either way. Okay, that's the half and half idea. Either this, or half of one and half of the other, or anything that adds up to 1. Okay? So that's just to make it clear what is going on with this field net here, this divergence-free laminar field net. Okay. Now, these are all pictures from chapter 10 of the review unit, so make sure you get it. Now, these half and half results here, the fact that the x derivative of the scalar part and the y derivative of the a part are equal, so it makes these two equal, or the y derivative of the scalar and minus the x derivative of the vector are equal. Okay, those relationships are general. The partial x with respect to a real of an analytic function, the partial derivative with respect to y, the imaginary of the analytic function, and then that function has an equality for that. And it has this negative antisymmetric equality for the flip of x and y. Okay, these are called Riemann Cauchy. You've probably seen that. That's what's behind this. That's what's behind these being orthogonal too, orthogonal coordinates. Presenting that as just a magic thing, that turns people off, I think. It makes you not really want to continue studying complex variables. Okay, now, what's analytic and what's not? This is, I think, a key point that I want to make before we go too much further here. Okay. We've already talked about the derivatives. Now I can rewrite a derivative with respect to z as that. And this would be true no matter whether the function was analytic or not. Same thing with this. Okay. But the criteria for a field to be an analytic function f of z is that it must not be a function of z star. Just as the Hamiltonian must not be a function, explicit function of velocity. Okay, that's similar to that, but that's a little bit of a stretch of logic, as we already seen. We had to do some funny analysis in order to make it clear what that meant. So here's the thing: df dz star, if it's an analytic function of z, is not a function of z star. That's what's letting us do all these tricks. Okay. And that then in turn implies that it satisfies the differential equations that we just stated. Riemann-Cauchy. Okay, and here's the sort of the proof for it. Now, we're playing both sides of the street here if you want. You can have your field be function of z star. In fact, that's what we work with. Okay? Then it must not be a function of z. This derivative has to go to 0. That turns into what I call the anti-Riemann-Cauchy conditions. The flips of these. So you can play that side of the street if you want to. Go either way. Okay? I just wanted to make that little extra thing that you won't find in either the math or the physics books that use complex variables. Now, here's a really easy way to test for being analytic of, say, z. The question is this thing, 2x plus iy, an analytic function of z? How do you check that? And in general, how do you check that? Okay? You test it using the definitions. Z is this, x is that, z star is this, and then y involves a difference with an I and a minus I actually over 2. There's a half coming in there again for those. Okay. So what you do to test this thing is you stuff in the definitions for x and y into your analytic function. If that's the way you were given it, you're already given it in the z and z star function. You answer this very quickly. But here I go and I put in those definitions for x and y. And then I just work it out, see what I get. It's z plus z star, okay, and then I get the I sort of cancel here, so I get a 2z minus 2z star, okay. I get 3z minus z star. The answer is a big fat no, because it's a function of z and z star, so it is not an analytic function of either. Now the impression you get when you study complex variables is analytic means that it's finite, and then it's non-analytic when it has some sort of cut or hole or infinity or something like that. Well, that's true, but this is the real guts of it right here, is the dependency. The Hamilton-Lagrange, conundrum of independent variables. Okay. How about x squared plus y squared? Again, no, that's z star z. Okay, forget it, okay? How about the one that we've got here, x squared minus y squared plus 2ixy? Ha-ha. Yes, indeed. I stuff it in there and I get z squared. That's an analytic function of z, but not z star. Does that clear up some of the bookkeeping rules, as it were, of this crazy stuff? Okay. I wanted to, get these things out in the open before we do too much with this. And the too much is let's do some integrals. This is what's really cool about this. What do those contour integrals really measure? Physics, you know, this is physics we're talking about here. How can I get this, drag this stuff kicking and screaming over and make it nice for physicists? So that's what we're really up to here. So we're asking a potential, just a difference between it at different points, to be an integral of some force with respect to the two-dimensional z. So that means that we're going to have a difference in scalar potential, and that'll be the real part of this difference, and then the imaginary part will be the difference in the vector potential. Okay? How does that come about? That's really what's involved here. So here's what you do. Remember, we had to take a given function of z, like z, and make it into z star, okay, in order to work with it and call it our, what we're going to talk about as a force. So this is the kind of function that we'd be integrating. But that's not what this is. So to make it so it's like this, I do a star twice. The stars cancel each other to give you this. Okay? Then I go ahead and start expanding it, leaving this guy there and putting this guy in there, and multiplying the real and imaginary part for this one with the real and imaginary part of dz. That's this guy right here, dx plus I dy. Okay? So when I get done, I get a little minus sign on that. Okay? And I have to be a little bit careful here. I think that's right, yeah. Yes, because this is a real thing, this is a real thing. So the star is not affected. It only affects the I, turning it to minus. Clear? Okay, so I separate those out, and here is a very simple Gibbs expression for part of this integral. It's a real part. And then there's this part here. It looks like a mess at first. Okay, that's the one that has this sort of funny cross product of differentials. And what I'm seeing right there is a typographical error that will be fixed very easily. I'll try to do that right in front of you. I somehow missed that. I'm going to escape from here. This is already in Keynote. I should be able to get that thing to come out right by just simply clicking on it. And it should open up for me the math type, but maybe that won't happen because this is that other machine. Oh dear. Okay. Well, this darn dot product is one of the things that got lost in the fight between Apple and Microsoft. But it's embarrassing. Okay, I don't know why I didn't see that. This is, you know, the new version of Keynote, and the old version used a symbol that the new one doesn't know. Okay, let's go ahead and go back to playing this thing, and it won't hurt it too much to go there. The basic idea is to turn the dot and cross product around so that you get the integral f dot ds. And so what you have to imagine is not just the contour where you're worried about the projection of the force field onto the differential of the contour, dr. That's our good old-fashioned work function that we're used to as physicists. The hydrodynamicist is more interested in where the fluid is penetrating, that is the projection of F onto the normal ds, an F dot ds. So little surface coming out of the screen here, unit height, differential length, being integrated over to give that. So the imaginary part of this integral is the flux integral. This is just the line integral. And I think that is really cool, because to have that ds, which is dr cross ez, normal to dr makes a little area that would you imagine coming out of the screen on top of that contour little unit. Fence, as it were, a fence that the flux can go through and get counted with the thing. So that's the deal here. Now all of these curves that are produced by this program here have other versions, you see. And notice when I move I get the forces and vector potential and all that kind of stuff written out numerically. But let's go back here to this, and let's plot in 3 dimensions the scalar function that we drew. Scalar function of the field, and that's this thing right here. Now, this thing lets you rotate this, and so you can see what it is pretty easily. You can see the topography lines, that is the voltage lines, if you were the scalar potential lines, the reds, okay, are very obviously topography lines, and this is the up here is the actual scalar potential of this saddle point. The saddle point being at the origin there. I'm going to try to rotate the thing up so that it shows better. You see that? So that making sense. Now these once again, these are things we're waiting for the new computer program to make so easy to see and to manipulate. There, that's probably giving you a pretty good picture of the actual quadrupole surface, the scalar part of that surface. Okay, so now of course, behind the scenes there's the rest of the saddle, so that kind of makes a mess of the drawing. But there's enough here that lets you see that. Now the alternative to that is to ask this thing to be plotted in 3 dimensions. That's mono is what it's looking at right now. If you want to look at it from your desk, you do a cross-eye, and then you plot either the scalar or the vector, you see, and then you can move either one of them and let it things, and you can zoom in to make it a little bit bigger, so that you have a stereo view. Now the way you look at these things is you go get your textbook and just put your face there, so your right eye is here and your left eye is here, and pull back from it, and try to keep your right eyes oriented that way so the image swings together into 3D drawing. Okay, or you get 3D glasses. You can borrow the ones that are in the back row there. But that's the key to this. Now, perpendicular to those topography lines, and I can probably show those better by just tipping this thing up like that, almost like that. Now you can see the red lines are all in plane, right? So basically a topography line is made by just slicing through that surface. Where it bleeds is the red, right? Now, I should have put them on the right place so that that topography line would have a partner over here. Obviously I don't, because we sort of did that randomly. But you can see they're all in a plane, right? All those hyperbolas are in plane for constant phi. How the heck do you do that for the vector potential? Okay, that's where this gets weird and fun. Okay, so right now what we have are the topography lines in red, and then the water, the blue, flowing perpendicular to them from here, if we were physicists, from here down, missing the singular point at the saddle, and flowing down on that side, and then others missing and coming down on this side. And we missed drawing them on right there. Okay, does that make sense? I mean, I want the visualization of this is pretty important. Okay, so see if there's anything else here I need to say. once again, reminded this is a coordinate system. Queer variable number 1, queer variable number 2 are scalar and vector potentials. Okay? Real numbers. All right? This is all real number here. Okay? For this particular coordinate system. I'm going to ask you to do Kajobian and Jacobians, but they better come out simple. They better come out with the same number here as here. And they always better have a 0 off diagonal. Okay? That's if they're analytic, right? If they're not, oh, then you can do anything you want. Okay, so that's the deal here. And also, the relations that give you this orthogonality, that's also what's coming here. Phi dot EA, those are little unitary vectors that are shown either the rows of the Kajobian or the columns of the Jacobian. And here you can name them either way, but you be consistent. And you will get the force vector out of either the curl of this or the gradient of this. And that we've already been through. But it also is showing us that these are orthogonal. That is, this guy dot that guy is orthogonal because of those analyticity relations. And then they all satisfy the Laplace equation. Either component, the A's or the Phi's, satisfy Laplace's equation in terms of x and y. So those are two things that that are important here. Divergence requirement is Riemann-Cauchy. Okay, so here's where it gets fun. And we've got just a few minutes here to do this, so let's go fairly quickly here. There is one particular potential out of all of these. If I have an AZ to the nth power, and then I'll have a power law of potential just by integrating, except for this case. This is a weird, wonderful case. N equal minus 1. Okay? The monopole. 1 over z. Okay? That's the one that doesn't have a polynomial field. I'm sorry, a potential field. Okay? This guy, source A, monopole field F, 1 over z. I integrate that, I get logarithm. Okay? So what I'm going to do here is I'm going to integrate it, and I'm going to just write it log z. But what takes the log of z? You've got to work out all of the algebra that goes with log of, put it in polar form. Aha! That's the way to get it. Okay? So that's what I want to do next on the screen here. And as I'm saying here, lecture 12 here today may end here. But let's take a few minutes over our time and go up to the to this thing here and select that particular case. And what I want here is function of A. There it is, the monopole right there. Okay. So I'm going to pick that, and it says. Make changes but save all the curves. I definitely don't want to do that. Erase and make the changes, and then what we're going to do is we're going to draw the vector potential. First the vectors, and then we'll do it real quick here by doing both at once. Plot both the phi lines and the A lines at once. I'd be a little careful when I do that. But here, I think I can get away with it. I'll just go up the road right here and show you the obvious circles for the scalar potential. And I'm just putting a whole bunch of blue lines on there. And then I'll go around here and make some gray lines. So this is a very famous orthogonal curvilinear coordinate system. It's called polar coordinates, right? And we get from 1 over z. So z was a little bit surprising if you didn't know about the quadrupole. And each time I'm doing this, I'm getting extra line on the red because I'm not quite hitting the thing straight away. So let's get this guy drawn, and then we're going to throw it into 3D and see what it looks like. So it's memorizing all those curves for this thing. And now I go back to main control here, and let's do the scalar first. There she is. Beautiful. With the lines that we put on there, right? Remember when we drew the inverse of the exponential to make a logarithm? And how I pointed out that they really stick together? Now you see why, right? I mean for physics, for the physics of this. This is the morning glory, right? Not a black hole, it's a black point. Okay? And zoom that up a little bit so you see that fairly clearly. Okay? So that's this thing done in 3D. And there's the logarithm of r as a real part. There's the angle. And that's the one that makes this function so important for doing all kinds of weird mathematics of integration of real variables that are pathological. Now, what I'm going to do here is show you that if I had done an I times z, I would get a situation where the circles were the blue, the flow lines, the things, and the red were the voltage lines, the scalar potential lines. So those are two opposite things. We can spend some time next time drawing a little bit of that. But what I am most concerned with here is I want to explain why the integral of this thing in that direction is weird, you see, because this thing just keeps going and going and going. It's just an angle theta. So you spiral up with that. And to show that, I'm going to simply take this one, go back to the main control here and say, I don't want to see the scalar plot. I want to see what the hydrodynamicist looks at. I want to see the vector potential now. I want them to be the equipotential lines. Okay, and this is what you get. And this is where it would really be nice to have, you know, a true three-dimensional picture here where you don't interfere with the stuff behind there. But I'm going to bring it around here where I think we can see what we've got. If I open it up on this side, I think you'll see what it is that you're looking at. You see all of the constant A lines are stairways on a helicoid. So when you integrate around this guy, you're going to go jump by 2 pi in this direction every time, and that means 2 pi I for the real integral. You see, this guy right here is a spiral that connects to that guy. That's the jump that it does when I declare I'm through plotting you. Go back and start over. But this never starts over. You see, this just keeps going and comes from minus infinity down here. It's just proportional to that angle theta. So however many times you want to go, be my guest. And each time you're going to pick up another 2 pi around that. So that's the idea that the contour depends on what contour you took. If you go from this point to that one right there, just by integrating there, no problem. You can have any path you want as long as it doesn't get near that singularity. But if you go like this to that point, you've picked up 2 pi. in addition to what you had before. So these are 3D pictures of what we're kind of looking at there, except that that one, there's the one where it's drawn the other way. So here's the morning glory now with the water flowing on the blue lines in or out of the orifice here. Then the flip of that, the actual vector potential of that, has the staircase that we're looking at in that picture. Here is the neighborhood of a vortex. That's what that is. Or it's the neighborhood of the B field of a wire coming out of here. If you want to do a magnetic field plot, that's what those green lines would be there, and then you'd be talking about magnetostatic potentials. And a vector potential is a much better description of that than the scalar potential is. But either one, it's okay. And you can see that by what we've done so far. Okay, I think that's about it. Now, one of your problems is to work out a situation where you have a complex number, alpha over z. And this thing turned out to be really helpful to people that are studying galaxy spirals right here, and we're one of the centers for that. So the coordinate system that you get, both of them are helical spirals that aren't perfect helixes or perfect circles. Okay, so that's the thing that we'll do, and then we'll take up higher order poles and things like that on the next lecture Thursday. Okay.